So now have a look at today's daily question. 3.10 Minimum height trees. A tree is an undirected graph in which any two vertices are connected by exactly one path. In other words, any connected graph without simple cycle is a tree. Without simple cycles, no cycle. Otherwise, it's a graph. Given a tree of n nodes labeled from 0 to n-1 and an array of n-1 edges where edges I equals ai bi indicates that there is an undirected edge between the two nodes ai and bi in the tree. Like this, 0 to 1 0 1 2. You can choose any node of the tree as a root. When you select a node X as a root, the result tree has height h. Among all possible rooted trees, those with minimum height are called minimum height trees. Minimum height trees. Return a list of all minimum height trees root labels. You can return the answer in any order. You can return the answer in any order. The height of a rooted tree is the number of edges of the longest downward path between the root and a leaf. Between the root and a leaf. Between root and a leaf. Root and leaf. Root and leaf. Yeah, root and leaf. Root and leaf. And root and leaf. If 5 is on the top, then the height is 4 layers. So 3 and 4 is the return value. Yeah. And if 1 is on the top is a root, then the height is 2 layers, and this is 3 layers. All others are 3 layers, so the return value is 1. 2 examples. Not very hard to understand. Constraints. N length, ai bi range, 0 to n-1, ai not equal to bi, so no self-directed edge. All the pairs ai and bi are distinct. No multiple edge. The given input is guaranteed to be a tree, and there will be no repeated edges. No repeated edges. Easy to understand, but a little not so easy to implement. Let's have a look. Not draw the picture. Draw something about this. The first is 0 and 1 0 2 3. So obviously there is a root. Yeah. And the second 3 4 is the center, and they are connected, and 3 have 0 1 2 0, 1, 2, 0, 1, 2, 3 leaves, and the 4 have a 5 leaf. This is somewhat easy. First, how to suppose the one have some children. The node 1 have some children. So like this, x, y, z. Then what's the middle? It should be 3, right? Then it should be 3. So think of the last state of our operation, and the operation we will take to simplify the problem one step forward. One step forward, we can cut all the leaves, all the real leaves of this tree, of this graph. At this time, we don't know what's the center and what is the remaining nodes. Cut the leaves. The first step, cut leaves. We call it cut. And after this, we will the first example 1, we will get 1, and this is the return. Yeah. And the example 2, 1 has no. If 1 have the node 1 have no children, then 1 is cut in the first operation, and the second 3 and 4 are returned because we cannot cut anything. Yeah, they are at the same layer, so return 3 and 4. So second, the end state. Suppose there are 3 nodes, just like this. We cut x, cut y, cut z, cut 0, cut 2, cut 5, and we get 1, 3, and 4. Then the second cycle, we will cut 1 and 4, and the remaining node is 3. This is the return value. So there should be no more than 2 nodes in our return list. Yeah, in our return list. Return a list of all minimum height trees, root labels. We should not return more than 2 nodes, either 1 node or 2 node. No more than 2 nodes, because if there are 3 nodes, suppose it's x, and this is y, and this is z, then they must have a middle, because there are no cycles. If there is a cycle, then we cannot delete any of them, because they are at the same layer. Yeah, but if there are no cycles, then we should delete the node x and the node z. Delete from this graph, and we get y. Y is the return value. So the end state is either 1 node or 2 node. No more, no less, because there are at least 1 node. Yeah, at least 1 node, and no more than 2. Such as 3 nodes. 3 nodes, there will be a new center. It is the root, and the other 2 is deleted. So the thing is somewhat not so complicated. This is the step 1 is a loop. Yeah, we keep cut every time we cut all the leaves, and find all the leaves and cut them, from the tree, and then we check it is at the end state. If it is at the end state, we just return. If it is not, we do the first operation again, first step again, and at last we return either one node or two node. So this is the main idea, the solution. But at C++, we need some data structures to implement this. We need to remember the node. This is a node. Yes, when we delete this, because the data is only remembered, is only given the edges. It is only given edges. We get these edges. So when at the first round we delete 5. Suppose they are x, y, and z. At the first round we delete 5, 0, 2, x, y, z. The first round. Then at this point, the 4 becomes the new leaf. How to detect the 4 is the new leaf? How to detect? I will use the unordered map and integer as a key and the value unordered set, and I delete this from our nodes, from our tools, because from one node there is a, suppose we make this edge. To this edge can be represented by two directed edge. So let's implement it. I have written it before. This is a medium problem, but not so easy and not so hard. Let's write it. There is a special state that if there are no edges, then we should return 0, no edge. And this in this state that there are only one node and it is labeled 0, node 0. We use this to save the tools from this node to where, and use format the edges into the change the edges into two directed tools. Then the tool is formed, and we need to get the other leaves. And we want to save the other node which this leaf is connected to. If the true size is only 1, then we add the from and the to's, and this time the two have only one element. So this is all the leaves we get, and we delete them from the from our tools. And we delete from the other node. We need to know the other node, otherwise at this next time the 4 have two directed out. We delete this edge, and then next time the 4 will have only one edge out. So we will know that the 4 is becoming the new leaf. Yeah. If the layer, if root 3 is the root, the only root, just like this, have x, y, and z. So we deleted the two from deleted the leaves from our data structure, from our memory, and then check if it is at the end. If it's at end, then this will break out, and we will form all the data to now return. Just need the from, don't need that to at this point. So I have a test. Yes. Not so hard to understand, but not so easy to implement. In C++, you can this may be optimized to one step, and the ordered map is not so efficient when you add and delete elements from it. So it's not very fast. If we use more memory, use fixed memory, yes, then this will be much faster, but we will do more search. and I cannot get the size directly. Yeah. Have I looked about the solution here? There are many more or less the same. Cut from the leaf is the main idea of this main solution to this question. And the different language have different data structures we may use, or we can optimize this to a queue outside the while loop. We can take some optimization here. Yeah. So time complexity. First, we notice all the edges. It costs O n because the edge size is n minus 1. Yeah, n minus 1. The size of the edges is n minus 1. So it costs n. Don't put every element. And then we trimmed every node from the tree, and every time we will loop every node once, and get it. This is only the leaves. So it is not guaranteed it's a binary tree. May have more than 2 children, many children here, 4 children here. So, and if 3 is the root, also 4 children. And it can also be only one liner. Yeah. So we need to cut at the worst state. The graph may look like this, a liner. Yeah. Like this. Connect this, connect this, connect this, connect this, and we may cut. Return this. Yeah. So slow, because every node we will get every element of this. At most, where the while loop will be done at most n divided by 2 times, and every time we will visit every node of this n. So m to the power of 2. So it's O n to the power of 2, and the space complexity. This not only to 1 or 2 nodes, so I will not add this to the space complexity. I have made this in 1 or 2 elements, so I will not count this n minus 1 plus 2 1. Like this. The size of edges is n minus 1, and the size of, so this total cost is n minus 1 plus 1 plus 2. Yeah, because every edge can be turned into 2 directed edge. Step 1. And this is the inner cost. I will not add to. Step 1, yeah, at most 1. So 1. Okay. Have a look at this question. This is somewhat interesting. We cut from the outside and found its center. I don't know if there are some solution that's more smart. Maybe. Okay, so this is today's daily question. Thanks very much.